I hope some of you tried this, and hopefully some of you got it. But what I want to do now is go back. I want to go over test 4, or at least go over the highlights of test 4. And then what you could do is you can take a look at what you did and compare to see where you may have gone wrong. I mean, not everybody went wrong on every question, and a couple people got everything right. So, I'm talking to. Let's see, where'd the test go here? Can you flip back and forth between the test and the calculator? So, question number 1. It's probably good if you pull the test up in front of you right now, but it said it is found that when 15 milligrams of a new drug is administered to humans, that after 7 hours they have 4 milligrams left. So we start with 15. So A sub 0 is 15. And after 7 hours, we wound up with 4 milligrams. So the amount after 7 hours is 4 milligrams. So when we put that into the natural law, it looks like this. That's the end amount, start amount. We don't know K, and that's 7. So we solve for K. That's the first question, which is the elimination rate. So let's go ahead and we'll divide both sides by 15. Take the natural logarithm on both sides, so we get ln, right? We'll calculate that in a second. And then divide by 7. So K is equal to the natural logarithm of 4/15 divided by 7. Now, of course, that's the exact amount, but let me just go ahead and do the calculation. I cannot find my, where'd it go here? I cannot find my regular scientific calculator, so I'm using an online one. These tend to be fairly awkward here, but I just need to calculate the natural logarithm of 4/15 divided by 7. So let's see here. To bear with me while I do this. By 7. Okay, so negative 0.18. So K for this particular drug is negative 0.18. It's definitely going to be negative because, like we said, K is negative, you get a decreasing amount. K is positive, you get an increasing amount. And a drug is being metabolized by your body, is being eliminated. So you're going to have less and less and less of it. Okay, so let's see. Now, this is a multi-part question here. So let me see what the next question, or the next part of the same question was. Use the natural log growth of K as a reasonable model. Okay, that we wish to keep a patient's level. What's the value of K? Yeah. If we wish to keep a patient's level between 20 and 8 milligrams, so you want it to go between 20 and 8. Same value of K. Same value of K. Let's go back to this equation. We want to keep it between 20 and 8. So we'll start with 20, and we'll end up with 8. So 8 equals 20 e to the negative 0.18 t, and we're going to solve for time. Because the question is, how long will it take? How long will it take for patients, the level of the drug in their system to drop from 20 to 8? And then we'll give them 12 more, and they'll bump back up to 20. So let's divide both sides by 20. That's 0.4. Take the natural logarithm on both sides. It's the same thing we just did. Mathematically, it's the same thing. We're solving for time before we solve for K, so it's not the same physical quantity, but the mathematics is the same. So here we get negative 0.18 t, and divide both sides by negative 0.18. So the natural logarithm, 0.4 divided by negative 0.18. And let me go ahead and do that calculation, and we'll see what we get here. Okay, back to the awkward online calculator. Natural logarithm of 0.4. Like I said, I actually prefer old style handheld calculators. It just seemed to work easier for me, but hey, whatever you can get a hold of. 0.18. Okay, so I'm going to round off just to 5.1. I'm not going to worry too much about rounding right now, but in the real world, you'd have to think this is hours, right? So it wouldn't make sense to go out to 5 decimal places. I mean, how accurate are you really going to be in the interval between when you give this person this drug, and also the fact that honestly, with living creatures, including human beings, this value of K usually is really an average, mean value, and it can even fluctuate within a given person. So this is not perfectly accurate, but it is a reasonable model. So that's the next part is 5.1 hours, and let's see, there should be one final thing here. Yeah, it is decided that we will give patient 20 milligram shot and a subsequent injection every 6 hours. I mean, this is pretty awkward. 5.1, a tenth of an hour is 6 minutes. That's every 5 hours and 6 minutes. I mean, how would anyone keep track of that, really? I guess you could, but 5 hours and 6 minutes, take the next dose. 5 hours and 6 minutes after that, next dose. So now what we're saying is that the value K stays the same, but we'll start off with 20 milligrams, and we want to know how much we'll have after 6 hours. Times 6. So this is a straight calculation. We don't do any algebra. We just have to throw that into the calculator. So let me go ahead and do that. Do this calculation here. Let's see. What do we have? 20, and then times e to the negative 0.18 times 6. I have to find the negative sign out here. Some calculators, okay, they let you use the subtraction symbol for creating a negative. Others, they have a separate command for negative, so just make sure you're aware of that, depending on which calculator you're using. Okay, so 6.8. So the amount after 6 hours would be, what did I just say? 6.8. That'd be milligrams. Okay. So to get back up to 20, we would give you what? 13.2 milligrams every 6 hours. And so that completes that question. The next question, people did pretty good. That was on the bacterial cells. And if you notice, really mathematically, that was exactly the same as question number 1. Same thing with question number 3. So 1, 2, and 3 all use the natural law. The math is all the same. Different underlying physical phenomena, but the math was the same. Now, question 4. If we invest 50, now, yeah, this is different, a little bit different here, but if we invest $50 in an account earning 7% per year, compounded monthly for 20 years, how much will there be? Okay, so this requires a different formula, and it's one that I went over in the video, but it actually is the formula banks use, so it's not, I didn't create it just for this classroom or something like that. And it's one that I think I have memorized. I have to say, this formula here for money in a savings account where it's compounded a given number of times per year, it's probably not the only application of this formula, but it's the only one I know. So this formula doesn't have really widespread applications. So it definitely, this formula does not rise to the occasion of, it doesn't meet the criteria where I would say, oh, you should memorize this. Okay, so it's the initial amount times 1 plus R over C raised to the power of CY, where C is the number of times you compound it. I wrote this formula down. I remember we went over this in a previous video, and I think I mentioned then, write it down or know where to look it up. It's really not worth memorizing. I've derived it so many times, I think I've accidentally memorized it. So this is a case where I said we initially put in $50. This is the initial amount. And the interest rate was 7%. compounded daily, so that's 365 times a year, and 365, and I think I said 20 years. Let me just double check that. Is that what I said? 20 years? Yeah, 20 years. So this is the amount after 20 years. Now this again is a straight calculation. I'm not asking you to solve anything here. So let me go ahead and do that calculation, and we'll see what we get. Again, I'm just going to throw this into this calculator. Hey, it's kind of weird. It's always not weird, but completely relying on a calculator to do something can be unnerving. But especially this online one here that I'm not completely familiar with. But 1 plus 0.07. My dog's scratching the door trying to get in here. I think if the dog knew what I was up to in here, it would be so anxious to get in here. Let's see, raise the power 365 times 20. And $202.73. Make sure I got the number. $202 and what did I just say? 73 cents. Okay, so this is just straightforward calculation. The derivation of that formula, remember we did go over that. It's the kind of thing, that's one of those, I think, once in a lifetime things. It is good to go over that derivation once in your life, and I hopefully followed it. But excuse me, it's COVID, no. It's not the kind of thing you'd ever want to do twice. Okay, now part 2. Oh my god. Hey, where'd my test go? I just I clicked on the wrong thing here. Okay. How much money will it be if it's compounded continuously? So now, and I pointed out, it means you can use the natural law of growth and decay. So if we use that, we're using our natural law of growth and decay. We get the amount after 20 years is the initial amount times e to the 0.07 times 20. Now, it'll be more, but it won't be a lot more. So let me do the calculation, and we'll get the exact answer. The more often you can compound it, the more you get, but there's a limit to it. In fact, this is the limit. It's actually where you're compounding an infinite number of times per any given time period, which might sound crazy at first, but that's actually what's going on. So hopefully you take calculus someday, and you'll find out more about that. 0.07 times 20. Hey, that's like, it's a funny calculation. Once I go to a calculator, I feel like my brain shuts off in some ways, because this is incredibly easy to do. See, my brain can think of several different ways of doing this. Imagine it was just 10. That would be 0.7, but you double that, so it's 1.4. But I was about ready to throw this all into a calculator, which seems like highly unnecessary. Hey, another way to look at it would be, if that was 7 cents times 10 is 70 cents, and then you double that, $1.40. Yeah, there's a whole bunch of different ways you can look at it. So say 1.4 and 202.76. So this is 202.76. So notice it's about 3 cents more. Nothing to write home about, but it is more. So hey, there's that one there. So those are just straight up use a calculator problems. Now, number 5 about the earthquakes here. Let's go over this one. There's definitely some confusion on this. Let's see, earthquakes. So the magnitude, this I do have memorized. This is, it's the Richter scale. So I think I mentioned it before, as in the Richter scale. I think it was a guy named Richter. I don't know much about it. Hey, I'm not a geologist. So what letters did I use here? Because you might get people using different letters. I used I and B. Well, not my favorite choice. I don't know why I used that, but at any rate. Now, what B is the base amount. It's the amount of energy it takes. It's really energy per time period. But I don't want to go down the rabbit hole of physics. Actually, I kind of do, but let's not. So let's just say this is the smallest quantity of energy it would take to make a just barely detectable earthquake. Any less, and you can't even tell there's an earthquake. This would have a value, but we don't need it for our purposes here. If I was a geologist, I would probably this would be an agreed upon figure, and I would probably know what it was. This is the amount of energy that went into the earthquake in question. So let's see, how much stronger is a 9.1 than a 5.4? Okay, so watch here. If we have what were the two? 9.1. If I take 9.1, and let's just say I said I for intensity, which is what a lot of books use. I mean, it's a pretty vague term in this context, but we'll just leave it at that. 9.1 divided by that base amount, and let's solve for this. Remember, with a common logarithm, if you don't write the base, it's assumed to be 10, and I'll use the definition of a logarithm, the very definition of a logarithm. Right? So we have this, and then multiply both sides by this, so we get the amount of energy or the intensity required to produce a 9.1 earthquake is given by this. You know what? Actually, it would be kind of more reasonable if I write it like this. Now, 10 to the 9th is a billion, so this is a little more than a billion times the amount of energy it takes to make it just barely detectable quake. Notice, hey, when you go from a 0, threshold event to a 9, you're a billion times more energy. So that's why, with a 2, 3, 4 on Earth, you can barely tell there's an earthquake. There's a 6, some damage, and maybe the buildings are leveled, and a 9 is a catastrophe. Now you could do the same calculation, but what was the other earthquake? The other earthquake was 5.4, and of course now you would see it wind up with this 10 to the 5.4. And I did say divide one by the other. Good. I'm glad I gave you that hint, because in general, when you compare two numbers, you can either subtract them or divide them. There's many other ways, but those are many other ways. But those are two pretty standard ways. Like if today's high temperature was 75 and yesterday's was 70, you'd probably say, well, today was 5 degrees hotter. You subtract. If this person has $100 and the other person has 20, you might say that person has 80 more. That's subtracting. Or you might say the person with 100 has 5 times as much, and you would get that by dividing. So you can divide or subtract. In the case of this right here, it's sort of nice if you divide, and here, let me show you why. If you divide 10 to the 9.1 be 5 to 10 to the 5.4b. Look, the b's cancel each other out, and then we have the same base. You need to subtract the exponents. So what's 9.1 here, I'll write it like this. 9.1, remember, same base, subtract the exponents. So, what does that give you, 3.6? Okay. That's, and you can throw it in the calculator, fine. It's going to be, over 1,000. It's a little bit hard to tell, right? 10 to the third is 1,000, 10 times 10 to the 10. 10 to the fourth is 10,000. If I had to guess, maybe that'd be like 14,000. Hey, just for the heck of it, let me go ahead and throw it in a calculator. My just quick guess is 14,000, but where'd my cursor go? Here we go. I'm sure I'm up by some significant amount there, but let's just see. 10 raised to the power of 3.6. I just said the most bizarre thing. 10 to the third is 1,000. 10 to the fourth is 10,000. So it's between 1,000 and 10,000. And then I was thinking 3,000, but I said 13,000. No, what did I say? 14,000? 4,000, 14,000. So 3,981. So 4,000. Which is to say, this earthquake required 4,000 times as much energy as this earthquake. So because the Richter scale is logarithmic, every time you go up 1, it's a tenfold increase. It's a order of magnitude increase. Okay, let's see what else was on the test. That was probably the toughest one for most people. Let me just roll through 6 through 10 here. They're pretty quick. They're kind of one-off questions, and most people got these right. You know, good job and all that kind of stuff. But let me just go ahead and plow through these anyways. So the first one. Oh, and my hint was if you're using a calculator, you're probably doing them wrong. And what that meant is I was choosing really nice numbers. So if you use the definition of a logarithm, this is 10 to the x equals 1,000. Well, 10 times 10 is 100, times 10 is 1,000. Boom, 3. So x is 3. And that's what I meant. I mean, really no calculator required. It would be actually weird to use a calculator. You can, and you'll get the right answer, but it would make me wonder that you don't understand what's going on if you use a calculator. Now, the next one is a natural logarithm of e to the power of 3. Well, those two cancel each other out, like we've talked about. So there, that's done. The next one, logarithm of x equals 3. Again, remember I've said it, but I'll say it again. If the base isn't written, it's assumed to be 10. That's a common logarithm. Use the definition of a logarithm. 10 to the 3 equals x. X equals 1,000. Hey, that was why I erased. That was really the reverse, like the mirror image of number 6. So let me see the next one here. Oh, the next one, yeah. Let me go over it, and then I'll say where there might have been some confusion, I suppose. Shouldn't have been, but you know. So this is a natural logarithm, which is the same thing. Remember, base is e by the definition of logarithm, and that's the answer. I mean, that really is the answer. If you put this into a calculator, which some of you did, you got an answer. That's about 2.7 times 2.7, so whatever that is, I don't know, about 8. But that's fine, and I didn't take off of that. This really is the exact correct answer. But if you just went one step further and calculated it, that's fine. And the last one here, so again, no calculator required though. And the last one, the natural logarithm of x to the power of 2 is equal to e to the power of 2. Let's see, this is the same thing as this. And this would tell us that, whoa, did I actually ask you this question? Let's see. What's the definition of a logarithm? Tell me. This is e raised to the power of e squared equals x squared. Now, I've got to be really careful here. In fact, I think I'm going to throw this question out. Yeah, I don't know what I was thinking when I wrote this question. This is not the same thing as e to the 2e. Look, quick technical timeout. And oh wow, I can't believe I wrote this question out. Watch this. Consider the following. Watch. 2 to the 3 squared. If I write that like that, that's actually ambiguous because it could mean this or it could mean this. And let's calculate them. They're not the same thing. So this right here is 3 cubed is 2 to the 9th. And that's, I don't know, 4, 8, 16, 32, 64, 128, 256, 512. So that's 512. Whereas this 2 cubed is 8. This is 8 squared, which is 64. So they're not at all the same thing. Now, when I use the definition of a logarithm, it says that e raised to this power. So it means that equals this. And I want to write something down which is wrong. This is not the same thing as this. Which, who knows? Maybe I was having a bad day. I don't really know. If this was the case, then x would be e to the power of e. But that's not what it is. Remember, the rules of exponents say you have to have something to a power to be able to do something like this. But at any rate, this is not this is not equal to that. You know what? Let me try something else on this, and then oh yeah, what if we try a rule of logarithms? We bring this down in front, that hopping down in front property that we talked about. Let's divide both sides by 2. The natural logarithm of x equals 1/2 e squared. And let me use the definition of a logarithm. Okay, the definition of a logarithm, which would say e raised to the power of 1/2 e squared is equal to x. There's the answer. And you know, maybe we can try messing around with this a little bit. But that was a little bit trickier. Yeah, no wonder there was a lot of problems with that one on the test. So I think after I make this video, I'm going to go back and readjust the grades a little bit. This was a little bit of a trickier problem than I wanted to. The graphs, lo and behold, I think almost everybody got those right. Not a big surprise, because obviously you can just go to Desmos or any graphing calculator and type it in. Presto, you get the graph. All I can say is I hope you understand why the graphs look the way they did. So, I mean, I've talked about that in a previous video. So, okay. So, you know, hey, have a good break. You know, keep checking. I might post a couple videos on chapter 11 during the break anyways. I don't know if that's just a terrible thing for me to do, but might do it anyways. Okay. So, good night.